This is a introductory lecture on computer graphics boards. My name is Joseph Wunderlich, professor. We begin with some basic physics, color from mixing wavelengths of light, and the visible part of the electromagnetic spectrum is visible light that we see, that we've adapted to. It's creatures on this planet going around a star, a sun, that puts out peaks in that area and of electromagnetic spectrum, so we've adapted to that. Those colors. Additive color mixing is what is involved in the computer, as opposed to subtractive for pigments and printers. We've learned about that previously in the introductory course. We mix red, green, and blue, RGB values, and hopefully everybody knows how to count in hex and binary by now. And so RGB value of FF1100 would be FF is 255, so the maximum intensity of red. And then 11 for the green, which in decimal is 16 plus 1 equals 17 intensity of green, and then no intensity of blue, 0, 0. And so that mixes, gives a certain color. Our processing for computer graphics can be in one of a couple places on the or in the computer, in a typical PC. On the motherboard, it's called integrated graphics. If it's within the CPU, it's called an APU, accelerated processor unit. And this is usually a must for laptops to get everything all packed in. A separate board is called an expansion board. Goes in expansion slots, more powerful, and a must for workstation class machines and high-end gaming machines. Here's something we've talked about before with our slots for our cards and switching to serial packetized communication with our PCI Express. Here's a comparison of the different buses. Remember, a bus is how you connect all these things together. It's not a moving thing full of individual things like people. It's actually the roadway, if you want to think of it as something, and that connects everything together. So you see a comparison, different buses, different bit widths, clock rates, the bandwidth in megabits per second, and the parallel versus serial. So you see the paradigm shift there from all of the prior to PCI Express methods were parallel. Special memory you have on your graphics cards. You want parallel access of video information. You want to match speed to the refresh rate requirements of the monitor. You had video RAM, dual ported, one port for regular DRAM type operation, one port to supply fast stream of data to the monitor. Now we have SGRAM, synchronous graphics. It is a type of dynamic RAM. Contains a finite state machine. We'll learn about that in other courses. To create the pipeline, that's what makes the changes in the machine instruction cycle from one state to the next. It's what makes the pipelines go. And special graphics functions we'll talk about here in a second. And then, for example, filling an area of memory with one RGB value. So you want to be able to do things like that very quickly. You want to do everything quickly. This is a special functionality to allow graphics things to be done quicker than otherwise. DDR RAM, we already talked about that before. Double data rate RAM. Now here are 7 important things to, or the 6 main things anyway, and then other things. that you want to consider with your GPU. Like your central processing unit, you have a graphics processing unit, processor unit. The GPU, either on the typically on the graphics board. So the first thing is accelerates generation of images in a frame buffer, used for refreshing images as a bitmap. So all of the pixels, one giant frame, is stored in one place. And you want to accelerate the generation of an image in a frame. You have a pixel pipeline. So you have ways, and we'll talk a little bit maybe about this. We don't talk a lot about pipelining in this particular course. We design them in other courses. But you want to get one pixel after another very fast. In your raster scan, generate your image going back and forth very quick, draw it on the screen. Special instruction sets. We'll learn all about this in other courses. Programming and special instruction sets, designing special instruction sets for graphics. So we learn about different architectures, SIMD versus MIMD, single instruction, multiple data, multiple instruction, multiple data, SIMD and MIMD machines. Just for graphics, a special set of machine instructions. Facilitate shader programs, number 4, for texture, reflection, refraction, shadowing. So you have the software that wants to do that kind of stuff. You have the hardware that facilitates it. Facilitate geometric modeling, geometric primitives, triangles, circles, squares, etc. Then the translation, rotation, projection of the 3D onto the 2D screen. So the graphics processor unit is hardware designed to make all this work, and then facilitating sprites, right? Little things moving around everywhere on your screen, pre-rendered 2D images. So you want to memorize those 6 things. Other features: 64-bit pixel, high dynamic range rendering support, motion blur. We talked about that during imaging. If you go too fast, it makes people dizzy, so you have to put in what your brain would put in for those situations with biological processing of images. Also depth of field, advanced digital signal processing. There's whole courses in that you could take. CUDA by NVIDIA. NVIDIA is a great company, great corporate culture, dominating a lot of the graphics card development. And they have a special development language, it's actually a language. It uses C, C++, and certain libraries and runtime software to enable programmers to use the parallel processing capabilities of the GPU. And so now, like as we talk about multi-cores in CPUs, we're talking about also cores in the GPU, but they're a little different kinds of cores, and these are in NVIDIA, the CUDA cores, and they're programmable individually and as a group, like CPU's cores, but not quite as complex, even though they do very complex operations. So it's not a full general purpose processor CPU type core, like on the like in the CPU cores. CUDA cores can, however, be used for high-performance general computing. So people are doing that now. You can use just the graphics card itself as a high-performance machine, doing parallel processing, different grain size problems, and used for deep learning and neural networks. Works very nicely in parallel processing. Digital versus analog. This is just about some connections. So DVI, mostly digital, for your LCD screen. Analog, S-video, VGA, video graphics array basic standard for CRTs, which are pretty much just a footnote in history now. And everything's driven by RGB values. TVs and projectors can be digital or analog. Performance, very important. So when you want to select a product, you want to consider performance, certainly. And so you should understand how to compare. Now you can find a pixel per second or vertices per second. A vertice you see in the image here is a vertex of the edges of a shape, primitive. And you could find measurements certainly in the past of that. You'll also see measurements even recently about floating point operations per second. We all know what a floating point operation is. But most recently, and probably most relevant to what you're trying to do, is frames per second, FPS, frames per second. So now there's something I want you to look through slowly and analyze all the data and the criteria. Ask yourself what each of them mean, and go through and take a look at all of them. This is a place that reviews GPUs, GPU check, and this is their assessment here. So this is NVIDIA Titan RTX, and you can read what they say about it. And I'll let you read that little blurb. Then I'd like you to go through and take a look at the different criteria here, including things like fan noise. Maybe that makes a difference to you. Used to make a big difference to me. Some of these machines were extremely noisy. I've got several machines in my room right here now, and I can't hear any of them, which is nice. It wasn't the case in the past. All I can hear is my fish tank bubbler. And then just look at the different performance there in frames per second, different resolutions, memory size, and the cost per frame. They have this broken down by resolution also. They have an overall score. Then look at their testing methodology. Now that was the #1 pick that I showed you out of these following tables. Don't expect you to read every one of these, but I put them all in here just to be comprehensive. You can see, look at their testing methodology, make sure it makes sense to you and seems like sound testing methodology. And then compare. Here's your cost and benefit ratio. Go down them and see how things go here. Just take a look. And then this one here is an additional rating, and so take a look at those. And you can go on the link there if you want more information about this company, and then GPU hierarchy value chart, right? Let's take a look at all that. So do spend any extra time you have today preparing for designing systems to carefully consider this kind of decision analysis. And please go to that link and understand what they're doing there.